All right. So thank you very much for those student talks. Next up, we have a lecture from Dr. Tyson Littenberg, who's at NASA and also affiliated with the University of Alabama in Huntsville, right?
Yep.
So Tyson is an expert on all things Bayesian, all things sampling. He is very much a Dark Lord of the Sith in terms of numerical sampling. He is well versed in all of those techniques and is going to tell us a lot about these different techniques before Bence later at about 11 o'clock is going to give us more of a tutorial on those things. So Tyson, thank you very much.
Okay, thank you. So there's too much to cover in an hour, and instead of going full fire hose at you, I thought I would just pick two topics to focus on. And then if there's a little bit of time at the end, we can sort of show how these two topics really are the foundation for all the other sampling tricks that you might come across along the way. It all starts with Bayes' theorem, which I think you heard plenty about yesterday from Neil. And full disclosure, Neil was my thesis advisor, so we're probably going to say a lot of the things similarly, and you might be getting a little bit of a biased view here. But Bayes' theorem tells you how conditional probabilities relate to one another. So the lowercase p's are probabilities or probability densities. In most applications of Bayes' theorem, they're probabilities. In everything we're going to talk about, they're probability densities. And this vertical bar separates what is sort of the truth and what we're trying to learn about. So the right-hand side on the vertical bar is what we assume to be true, and then the left-hand side of the vertical bar is the sort of the dependent variable. So this term right here is the probability of A given that B is true, or probability density. All right, so just for pedantic purposes, I can pile on many, many conditions on the right-hand side of that vertical bar. And so now this is saying the probability that A is true given B and C. And you'll notice in Bayes' theorem that this, C appears on the right-hand side of the bar in every single term here. So there is a lot of stuff that you assume to be true, and it all lives on the right-hand side of that vertical bar. Why am I making a point of that? So if I recast Bayes' theorem now for our inference problem, now the sort of dependent variable would be like model parameters that we're going to call theta. And that is conditional on the data that I've observed being true and the model that I've used to parameterize that data being true. And so then you follow Bayes' theorem and you get this term, which is the probability that the data would happen if I had the right model and its parameters. So this is what we call the likelihood. I have a probability that the parameter would be true given the model, not thinking about the data. So this is what I knew about the model before I did any observations. This is the prior. And then we have this funky thing down here, which on one hand is basically just a normalization term to turn this whole right-hand side into a probability density. On the other hand, it looks like a likelihood. It's a probability that I would observe some data given that my model is true. So this is often called the marginalized likelihood or the evidence. Today, we're going to talk about sort of the foundational way to learn about this thing, the posterior distribution function. So what a lot of people call parameter estimation. And one of the foundational ways to calculate this denominator term, the evidence. Okay, hopefully that's a refresher from yesterday. So to hammer this point home a little bit more, we make up the likelihood function and the prior. We shove it into a computer and it spits out, depending on what we ask the computer to do, the posterior distribution function, the thing on the left-hand side, and or the evidence. Those are the things that we want. Once we have decided what our likelihood is and what our prior is, it's just a matter of turning a crank in order to find out what the posterior distribution is and what the evidence is. It's purely mechanical. Now, it's a really difficult job to make an efficient crank to turn, but once we've specified these two functions, the work is done. And now it's just a computational problem. And it's really straightforward to calculate, right? We've invented these two functions. We can calculate them anywhere we want in parameter space, no big deal. The trouble is, that doesn't really tell you anything because they're probability densities. So why doesn't it tell you anything? So if you had, so I like to make an analogy with quantum mechanics. If you have the wave function of an electron, that doesn't tell you anything about what the electron is doing. That just basically is a tool you use to calculate what the electron is doing. And the way you do those calculations is by doing integrals. And so the same goes for probability density functions. If you have a probability density function, the way you gain insight is by doing things like calculating moments, like the mean or the variance or skew or kurtosis, or name all the moments you want. And the way you calculate those things is by doing integrals. And integrals suck because they're really hard to do, especially if you have a large dimensional parameter space. Large dimensional integrals are really, really hard. So that's a drag. Sometimes, even if you have a large dimensional parameter space, you only really care about one parameter. The rest of them are nuisance parameters. And I'm sure Neil talked yesterday about marginalizing, where I take my posterior distribution function and I just integrate over all the parameters I don't care about to get down to a posterior distribution function for the one parameter that I do. Well, crap, now we have to do a bunch of integrals again. So while it's really easy to calculate these probability density functions in anywhere in parameter space, what we actually want to do is integrate them, and doing numerical integration is hard. Doing numerical integration for large parameter spaces is even worse. And so all of these algorithms are really ways of doing these numerical integrals efficiently. So one way to do that is say, okay, forget about trying to integrate the thing. What if someone just granted me a list of numbers that were all drawn from these probability distributions that I want to know about? So a set of values theta that are statistically consistent with this underlying probability distribution function, in this case, the posterior. So now I just have a list of values of these parameters. Well, now I can calculate moments the good old-fashioned way, right? Instead of calculating a mean by doing an integral, I can calculate a mean by adding things up and dividing by how many I had. And now life is good. And so the whole crux here is to create algorithms that will produce for us sets of random numbers consistent with these underlying populations, or sorry, underlying distributions. And then we can just be, really naive about how we calculate moments or do other characterization things from those distributions. Okay, so what we want is a set of independent, identically distributed samples from our target distribution, in this case, the posterior distribution function. So in the literature, these are also often called high ID samples. The types of functions that do that for us are random number generators. So what I want is a random number generator for this distribution, in this case, the posterior distribution function. You might have come across random number generators a lot. So a popular set of random number generators live in Python. In the NumPy module, there's a random number generator called normal, which just every time you query that function, it spits at you a random number drawn from a Gaussian. Or the uniform random number generator, every time you call that function, it just spits back a number randomly distributed between 0 and 1. So we basically want to create numpy.random.myWeirdFunction and have it return to us these samples that are just fair draws from that distribution. So to do that, we're going to take a step back into a little higher level of abstraction and note that random number generators are a subset of a more general class called Markovian processes. And that the bottom here is the magic behind a Markovian process, which is saying that the probability of being, so if this is like a time series of samples from 0 to n, the probability of getting sample n from my series can only depend on my most recent sample. So another way to think about that is this string of random numbers can't have any sort of history. It can't know where it was several samples back. Now, the best case, if you have a really, really good random number generator, is that it doesn't even depend on your last sample, right? Every time you call it, you just get something fresh. So random number generators are a type of Markovian processes, but Markovian processes quite aren't as strict. And so the sort of industry standard way of generating a Markov chain, a set of numbers that are Markovian, is using an algorithm called a Markov chain Monte Carlo. So Monte Carlo, so it's doing a bunch of random stuff. And Markov chain, it's doing a bunch of random stuff that's going to give you, at the end of the day, a Markov chain. So the statistics, the internal statistics of how this Monte Carlo is working are designed to make sure that the output has all these nice Markovian processes. All right. Stuck. Okay, so we're going to use this class of algorithms to generate a Markov chain from our target distribution. We don't care what the target distribution is right now, just any old probability distribution function. So the statistical magic that ensures that this algorithm gives you a Markov chain is this detailed balance condition. So this detailed balance condition says, let's say I'm currently at location X in my chain, and the next step I'm going to take in my chain is going to be position Y. The probability of landing on position Y, given that I'm at probability of being at position X, times the probability of being at position X is equal to all those things inverted. Does this look familiar? What's it look like? It's Bayes' theorem all over again, okay? So the detailed balance condition is just Bayes' theorem written out in one line instead of as a fraction. So the probability of Y following X in my Markov chain is something that we don't actually know. If we knew that, we wouldn't have to do all of this, right? So we're sort of trying to empirically figure this out. But if we don't know how to evaluate this thing, then it's going to be really hard to satisfy this detailed balance condition. And so instead, what we're going to do is we're going to replace this probability of going from X to Y, which we don't know, with some function that we do. So this function Q is going to basically do the same thing. It's going to tell us about the probability of going from X to Y, but it's not necessarily the one that satisfied detailed balance. It's just something we know how to calculate. We get to invent this one, okay? So this is commonly referred to as a proposal distribution, and proposal distributions that you might want to try would be, for instance, something that draws from a Gaussian, because NumPy has coded that up for you, or something that draws from a uniform distribution, because NumPy coded that up for you as well. Okay, so this is just going to be some function that's just going to generate random numbers for us in a way that we know how to calculate. So if I replace in my detailed balance condition those P's, which I don't know how to calculate, with these Q's, which I do, then it is no longer an equality, it is an inequality. And so, you know, it's a lecture when someone says without loss of generality. Without loss of generality, let's just say that the left-hand side of this equation ends up being larger than the right-hand side. We could have done it the other way, doesn't matter, okay? The important thing is that it's no longer an equal sign. So I've broken detailed balance by replacing that function I didn't know how to calculate, that P, with this function that I do, this proposal distribution. So now I have to fix it. And the way I fix it is by adding a fudge factor to both sides of the equation to rebalance so I get detailed balance back. So in this case where the left-hand side is larger, what I'm effectively saying is that the chain is too eager to go from X to Y and too reluctant to go from Y to X. So I have to give it a boost for going from Y to X, and I have to suppress it from going from X to Y. So I'm going to add to both sides of the equation these transition probabilities alpha, and these are numbers that have to be somewhere between 0 and 1, and they're going to just counteract the tendency for the chain to go one way or the other, so they get an equality back. Okay, so that alpha thing is the probability of transitioning from X to Y, given how I've defined my proposal distributions. And then the one on the right-hand side is the probability of transitioning from Y to X, again, given how I've defined these proposals. All right, so if we've already said that we go from Y to X too reluctantly, and alpha has to be a number between 0 and 1, it had better not do any harm. We're already having enough trouble going from Y to X as it is. So that number had better be 1. And then alpha is going to have to suppress the transitions from X to Y. So that's going to be a number that's less than 1. Okay, did that little sleight of hand make sense? So if this term is going to be 1, then I can easily solve for my other transition probability, and I get this ratio where it's the target distribution of where I want to go divided by the target distribution of where I am. And then it's basically reweighted by these proposal distributions of where I am or where I want to go depending on where I am in the bottom, in the denominator, and where I currently am depending on where it is I want to go in the numerator. So we're just going to define this ratio as this capital H, which is called the Hastings ratio. And that seems kind of silly because I've already said that this is the transition probability. So why did I bother giving it a different letter? And the reason that I call this thing the Hastings ratio is because we want to generalize. And so let's go back to that previous slide and reverse the inequality. And if I calculate that ratio, now that number is bigger than 1. But I said that the transition probabilities have to be between 0 and 1, right? So this Hastings ratio can take on arbitrary values, but the transition probabilities have to be probabilities. They have to be between 0 and 1. And so now I'll generalize and say that this transition probability is the minimum of either 1 or the Hastings ratio. So the Hastings ratio can take on arbitrary values. If it takes on a value that's greater than 1, then my transition probability alpha is just 1. Okay, and using that is the sort of central engine for how these Markov chain Monte Carlo algorithms work. So here's the Markov chain Monte Carlo algorithm in bullet point form. It only takes up about 4 or 5 bullets, which means therefore it only takes up about 4 or 5 lines of code, right? No big deal. So you start off with some random point in parameter space. We're going to call that X. You've invented your proposal distribution, and using it, you're going to propose a new state in parameter space. We're going to call that Y. Then you calculate the Hastings ratio, and from that Hastings ratio, you calculate this transition probability alpha. And then you have a choice to make. If you're going to accept this new state Y with probability alpha. So if alpha is, so if the Hastings ratio is greater than 1, for example, then alpha is 1. Then you're going to accept Y as a new state of the chain. If alpha is somewhere between 0 and 1, let's say it's 0.5, that means you're going to accept it with a 50-50% chance, or a 50-50 chance, right? So basically, if alpha comes back as 1, you adopt Y as your new state of the chain. If alpha comes back as something less than 1, you roll the dice and see if it was your lucky day, and you accept Y. And if you end up rejecting Y, then you preserve X as the state. And then you do it again, and again, and again, gazillions of times until some convergence criteria is met. And that is a lot of black magic, is deciding when the convergence criteria is met. But typically, you have to iterate over this, tens of thousands, maybe millions of times, depending on how complicated your target distribution is. So lots of rinse and repeat here. So now we want to map this to our inference problem. That was just very general, any old target distribution. You could come up with some funky distribution you want to generate random numbers from, or you can say, I want to generate random numbers from my posterior distribution function. And that means the state that I care about are the model parameters. And so then my transition probability becomes the posterior distribution function in the numerator of where I want to go, theta prime, divided by the posterior distribution function in the denominator of where I am, theta, and then you have the proposal densities there to help with the detail balance. Now notice when we wrote Bayes' theorem before, we also had in the denominator that evidence term. That evidence term is the same wherever you are in parameter space. It does not depend on the parameters, it only depends on the model. So it cancels in this ratio. So that's great because it's super hard to calculate the evidence. But that sucks because it means we learn nothing about the evidence by using this technique. So if I want to use a Markov chain Monte Carlo, I learn all about the posterior distribution function, which is one of the things that we want. But then I'm going to have extra work to do if I then want to learn about the evidence to get all of the terms in Bayes' theorem complete. Okay, so the best way to gain some intuition is to think about limiting cases. And so we're going to look at, I think, 3 different limiting cases of this transition probability of how this Markov chain Monte Carlo thing works. The first of those limiting cases is the nicest one to have to deal with, where you have a symmetric proposal distribution and you have uniform priors. A symmetric proposal distribution means that the probability of going anywhere in parameter space is the same if I'm going from A to B as it is from going B to A. So these proposal density terms in the Hastings ratio cancel because they're the same regardless of which direction you're going. That's a symmetric proposal. A draw from the prior is a symmetric proposal because it doesn't depend on where you are. So any proposal distribution that does not care where you're actually currently sitting in parameter space is going to be symmetric and will cancel in the Hastings ratio. Great. Uniform priors also means that they don't actually depend on your location in parameter space. You get the same value anywhere you are. So those cancels as well. And that means that our transition probability, our Hastings ratio thingamajiggy, reduces to a likelihood ratio. So it's just the likelihood of where I want to go divided by the likelihood of where I am. All right, so let's say my likelihood function is some multimodal thing like this. It's just a single parameter model, and I'm currently sitting at state theta. If I want to propose a move to theta prime here, the value of the likelihood is higher. That means the Hastings ratio will evaluate to some number larger than 1, which means the transition probability equals 1, which means I take it. In other words, you always go uphill. If you propose a move uphill, you go uphill. However, if my next move is at theta double prime, which is downhill, then I might go. I might not go. This ratio is going to be a number somewhere between 0 and 1. And so that encodes the probability of me accepting that. So usually the way you do it is you calculate this Hastings ratio thingy. You get a number somewhere between 0 and 1. And then you draw a random number between 0 and 1. And if the random number that you drew is larger, less than, if the random number you drew is less than what you got from the Hastings ratio, then you accept that. So that means you always go uphill, and there is some probability, which is alpha, of going downhill. And this is super important because this is the whole detail balance thing really in action. And this is what guarantees that an MCMC will eventually converge. That convergence might require the age of the universe to actually occur, but it's going to happen. Mathematically, it will always converge because it has this probability of walking downhill. If you just have a sort of maximum likelihood type of approach, there's a good chance it'll run up this hill and then just get stuck here and never know that there was some global maximum hiding at a different spot in parameter space. A Markov chain will eventually walk all the way down to this valley and then notice that there's a new peak to climb and very efficiently go up because it always accepts moves that go uphill. And so then it'll run up here. But then again, eventually it'll just randomly work its way down and sample between both of these peaks. Okay. In practice, to get something to sample some multimodal distribution efficiently takes a lot of work. And so now we'll look at that now. So our limiting case number 2 is when we were really, really lucky and the proposal distributions that we invented, these Qs, happened to match the target distribution that we wanted to sample. So in that case, so here's our, we're ignoring the priors for right now. So here's our target distribution is just the likelihood. So we're assuming we have uniform priors again. And then these Qs are actually going to equal the target distribution, the posterior. And that means that this transition probability is 1. And what that means, if the transition probability is 1, it means everything gets accepted. And so now I've invented my numpy.random. My favorite posterior distribution function. Every time I have the algorithm take a step, I get back a new place in parameter space. So this is the maximally efficient way of coding up a Markov chain Monte Carlo, is to know what your target distribution is ahead of time and just sample from that. Obviously, if you could do that, you wouldn't bother with the Markov chain, but you get the idea. And so what this should motivate in you is that to get these algorithms to work efficiently, you have to design very clever proposal distributions. That's where all of the work is. The algorithm is really easy to write down poorly. To get it to work efficiently, you have to design clever proposal distributions. So there's a whole cottage industry of different samplers that try to take this burden off of you and put it on the sampler. So a really popular one is MC. It's one of the first really popular ensemble samplers that you can just import in Python and run. What MC tries to do is it tries to learn effectively what a good proposal distribution is by looking at gradients of where all the samples are in parameter space. Those work out pretty well if it's not a particularly pathological function that you're trying to sample, and if it's not super, super high dimension. So basically, if you have, it's a slightly glib way of saying it, if you have a really, really interesting sampling problem, you're probably not going to be able to get away with something off the shelf. You're going to have to design the sampler yourself because you have to use a lot of domain knowledge to figure out what these proposals should be. If the sampling isn't the interesting part, you just want to get it done and then move on to the interesting stuff, then there's a good chance that one of these off-the-shelf samplers are okay. Keep getting stuck. Okay, the third possibility for our limiting cases is, let's say you were really, really good and you designed a proposal distribution that said, go to the right value. And that's your only option, right? You somehow knew what the right answer is. You knew what the truth was. And your proposal distribution says, just go to the truth. So your proposal distribution is going to be like a delta function between where you want to go and the truth value. This seems like a really good idea. Unfortunately, if you plug this in to the transition probability and turn the crank, you actually get a transition probability of 0, which is a little counterintuitive. And so the way I like to think about this is that a proposal distribution is kind of like a teenager, where the more and more that you encourage them to do something good, the more and more that they will resist you in doing something good. I currently have 2 teenagers. This is really hitting me deep these days. So if you look at the transition probability and sort of pull back, the left-hand side of the thing that's highlighted in red, which is the stuff that we invented, the likelihood and the prior, that's the part of the transition probability that says, if things are good in this new position, take it. And if things are bad, maybe take it, maybe don't. But then there's this counteracting force coming from these proposal distributions that is gonna basically negate how eagerly you are pushing the sampler in one direction or the other. So this is the term that sort of keeps your sampler honest. And this is the term that's just trying to, get answers for you as quickly as possible. Okay, intermission. We're going to take a breather, and then we're going to take a hard right turn. Do we have any questions about how MCMCs work deep down under the hood? Sophie.
So yesterday, Neil talked about using a differential, I think it was the differential evolution step where you look in your past history to see where you should go next.
Yep.
Does that break detailed balance?
It does. And then there's this sneaky thing that people do, which is say, yeah, but asymptotically, it converges, right? So if you're using the past history of your chain, then you're breaking detailed balance because the proposal depends on what you did. But if you keep updating that past history of the chain, and the updates are all Markovian, then you sort of, over time, you sort of lose that memory. And so it's a very hand-wavy, asymptotically converging kind of situation. But if you just like your first 1,000 steps of your chain and you filled up some buffer and then you were going to use that for the rest of time to do all of your proposals, then that would be bad. There's also when you update the proposal, the next step that you take is using the updated proposal, but the step you took before that was using an old proposal. And so then if you really want to be pedantic, you got to sort of use one for one and the other for the other. But again, that's one of those things where it just sort of gets washed out in practice if you do it, you know, gazillions of iterations. So it's okay to do that sort of thing. But yeah, by the letter of the law, it's just one step beyond. It's like going like 7 miles an hour over instead of 5.
Have any questions online?
Okay, onward. So the Markov chain is what gives you the posterior distribution function, and we've totally glossed over the evidence. And once you've run your Markov chain, then you have more work to do to calculate the evidence, and sometimes that more work is not very trivial. So what would be nice is if you didn't actually care about the posterior, you just wanted the evidence. It'd be nice if there was an algorithm that did that for you. And there are a bunch. The one that we're going to talk about today is called nested sampling, which was basically designed to calculate this evidence term. And then you have some extra work to do if you want to get posterior samples. So it's sort of the complete opposite of the philosophy of the Markov chain. So remember that this evidence is the integral over all of parameter space of the likelihood times the prior. So this is effectively the normalization so that your likelihood times prior turns into a proper probability density for your proposal. Another way to interpret it is it's like the average likelihood over the entire model. So it's telling you effectively how good your model fits the data, not necessarily how good your model fits the data if you happen to have the best fit parameters. So it's sort of more of a 30,000 foot view of how well your model is doing. Neil probably got into some of the nuances there. So this is a large dimensional integral. We've already complained that large dimensional integrals are really hard to do. And so the whole idea behind nested sampling and another approach for calculating the evidence called thermodynamic integration is to recast this as a one-dimensional integral because we know how to do those. So we're just going to assert that this is a one-dimensional integral, and we're just going to change the notation here so that it matches the literature on this stuff. So what used to be the evidence here is now going to be this capital Z. This capital L is going to play the role of the likelihood. And this volume element dx is the prior volume element. So it's the prior times d theta is this dx thing. Okay. Now this is a much easier integral to do, so we're in good shape. So this x is the accumulated amount of prior volume for likelihoods greater than some value lambda. I think I wrote that out. Yeah. So it's you could think of it as the fraction of the total prior volume or prior mass that covers the region in parameter space where the likelihood values are greater than some value lambda. Okay, and that means that this integral, the bounds in this integral are from 0 to 1, because you're either covering no prior volume or all of the prior volume. So not only is this a one-dimensional integral, but it's a one-dimensional integral with like really simple bounds of integration. So this should be no problem. So here's how you sort of visualize this mapping from parameter space into this idea of just like likelihood in prior volume. So at first, you have all of parameter space at your disposal. Can you not see my mouse, by the way? No way. I've been pointing with my mouse this whole time. That's funny. Okay, so here you have this whole prior volume. And so let's say that the likelihood is like effectively 0 because you're getting all prior, no likelihood. And the prior volume that you have enclosed in this region is 1. It's all of the prior volume. And so then your integrand is out here at 1 for all of the prior volume and 0 for the actual likelihood. Okay, now I can pick a spot in parameter space, any spot in parameter space, and evaluate its likelihood. And now imagine that there's some contour in parameter space of all the different values that have that same likelihood. That contour encloses a volume that is a fraction of the total prior volume. So that fraction of the total prior volume is going to be called x1. So now at x1, we've enclosed a certain amount of prior mass, and we have likelihood L1 on that contour. And now I can take another step, and another step, and another step, and eventually shrink my way down to a place where I've got the maximum value of the likelihood, and I'm enclosing 0% of the prior. And then this is the function that we integrate. And the area under this curve is the evidence. Great. So how does this algorithm then actually work in practice? So what you do for a nested sampling algorithm is you start with a large number of samples. These are called your live points in the nested sampling parlance, and you just sprinkle them throughout the prior. And then you initialize and say, I have 0 evidence, I'm covering 100% of the prior, and I'm at my first iteration. Okay, then you calculate the likelihood of every single one of the points that you've sprinkled onto the prior, and you find the one that has the lowest likelihood. And you record that value as this L sub I, and you keep track of the parameters that had the lowest likelihood in your ensemble. And then you wave your hands and say, well, the step from 0 to Li probably enclosed roughly something like e to the minus I over the total number of parameters I have in prior volume. And there are some hand-wavy arguments for why this is a reasonable choice to make. And there are better choices to make if you get really deep into it. And there are ways of sort of like empirically figuring out how much prior volume you've enclosed if you want to get really, really serious. But if you're just sort of like coding up a toy problem, this is a reasonable place to start. So you know how much prior volume you've enclosed, and you can update your accumulated evidence here with the likelihood. So this is basically like a, not even like a trapezoid integration, right? So it's just the likelihood, you know, the height times the width of that little step that I took in the integrand. And then I'm going to take my parameters theta n, that should be a lowercase n, excuse me, my parameters theta n that gave me my lowest value of the likelihood, and I'm going to sample until I get parameters that are higher in likelihood. And again, this sampling is something you can do lots of different ways. A lot of times the algorithm will just use a Markov chain and sample for a while until it gets a higher value of likelihood. And once you get a higher value of likelihood, you stop and you sort all of your likelihoods in all of your parameters, all of your samples in the ensemble again, and you find the one that has the lowest likelihood and rinse and repeat. So to recap, you put a bunch of samples out in prior space, find the one with the worst likelihood, estimate how much volume it would enclose, update the evidence, and then throw that one back into the pile. That shrinks the contour. You update the evidence again. You take the worst one, throw it back into the pile. The contour keeps shrinking, and you keep going and going and going and going until it has stopped. You have to supply the stopping criteria for this. It's not like an MCMC that just goes until you decide to kill it. You have to say, go this long. And then once you've gotten to your maximum number of iterations that you want to do, then there's this last ditch correction step, because now you have this swarm of samples, hopefully tightly clustered around the max likelihood value. And that's where you get a big contribution from the evidence. And so then there's this like last correction step to get that last bit of the integral right, assuming that all of the samples you have are basically each contributing to the evidence kind of equally. And so the two pitfalls for nested sampling are that you start with enough of these live points in the first place, so n is large enough, and that you've done enough iterations, so I max is large enough, that you get a nice robust convergence on the integral. So it doesn't have all of the nice guaranteed convergence qualities that a Markov chain does, but at least you're only going to suffer for a finite amount of time because you've told it how long to go. So then you've got your evidence, but you don't have your posterior. So the way to get posterior samples now is that you have what is in effect the normalization term on Bayes' theorem. So you also have a list of parameters, a list of parameter values from all the different places that you tried out in parameter space. And so you can basically put all of them into a bag and pull them out of the bag with the probability of their likelihood times their prior divided by the evidence. So you're reweighting the samples that you had to generate effectively a bunch of independent samples from the posterior distribution. So again, if you've done a really crummy job of converging, or if you've done a crummy job of estimating what these prior volumes might be, then you might not get the best estimate of, you might not get the best sample from the posteriors. So you might have to work a little bit harder on those things. But at the end of the day, this algorithm also works. Okay. So those are the two things that I really wanted to cover. And then there's a world of stuff out there. There are gazillions of other ways to calculate evidence. There are other sampling algorithms. I briefly waved my hand at ensemble samplers, but I think I've already gone for my allocated amount of time. So if you have any questions about what we talked about, fire away. If you have any questions about any of this stuff, you can also fire away. And then if you have deeper questions about any of it, then just find me, afterwards and we can talk. So what questions do you have before Steve kicks me off? Yes.
At the end of the nested sampler, if you're doing some kind of just rejection sampling using the live points that we already had, can you just keep on generating as many posterior samples as you want?
So it's not you don't just use the live points, because those live points have all just clustered around the max likelihood value. And you want to get the whole distribution. So you basically use the whole history, right? Every time you throw one back into the pile, you want to keep track of where it was and then resample that. So can you then just resample as much as you want because you know what the normalization is? I don't know, because you also have to keep track of that little volume element, the prior volume element, which you've sort of been estimating along the way. So that's a good question.
I know at least multi-nest used to give you just a file that had equally weighted posterior samples from this weighted scheme, and you couldn't control how many samples it would give you. It would just decide this was an appropriate number for this problem, and that's it. But it also gave you files of like the previous visited points along with their weights, so that you could do that yourself. They weren't equally weighted. You had to manually go in and accommodate the weights. But it was a bunch more points than the posterior sample that it actually did. I don't know what dynasty and alternate does these days, like what the output gives you. Maybe it's better than alternate.
I'm gonna say that there must be some fundamental reason why you can't, or else you would. So I don't know why, but there must be something in there. And I'm guessing it has something to do with that prior volume bit, but I'm not sure.
We've got some buffer time as well, so we'll take a break at 10:45. But if you wanted to answer more questions or get into other intricacies that you thought we wouldn't have time for, then feel free.
Okay, buffer time.
So in MCMC, there are tools that you can use to figure out if your changes converge pretty well, like calculating autocorrelation lengths or movement metric. Is there anything that you can use with nested sampling that's kind of similar to calculate the number of live points that you need to use to start?
So I think there are some sort of like rules of thumb that you can use to get a handle on the number of live points that you want to start with and the number of iterations. And they all have things roughly to do. So you heard a little bit about the KL divergence yesterday. So it's sort of a measure of how different the likelihood is from the prior. And you can use some hand wavy arguments there to sort of scale how big of an ensemble you need and how many iterations it's going to go. But in my experience, now I've never been a user of nested sampling myself, so I don't have a ton of experience. My experience is watching other people use it. And in my experience, it's much more empirical than that. You run it and then you're like, oh, crap. And then you turn everything up and run it again. Those sort of convergence tests you were talking about with an MCMC, you can use those on the output posterior samples. And if you fail those criteria on the output posterior samples from nested sampling, then you probably shouldn't trust the evidence calculation in the first place. So that's one way to sort of quantitatively check on convergence. And then there's the good old fashioned way of, do it and then crank everything up and do it again. And if you have the same answer, call it a day.
We take a question from online first. Then go back here. I've got a question from Tyler online. Go ahead, Tyler.
Yeah, thanks for the talk. How difficult is it, or how do you determine whether or not your problem that you're trying to answer is simple enough to use an off-the-shelf sampler?
Yeah, so that's a good question. So first of all, if your problem is fixed dimension, right? So Neil talked a little bit yesterday about trans-dimensional algorithms. I don't know of any off-the-shelf trans-dimensional algorithms. So if you're not sure which model you should be using, and that's one of the things you want to sample over, you have a lot of code to write. So let's throw that out for a minute and just focus on the fixed dimension case. I would bet if you dig into the Dynasty or the MC documentation, there's probably a suggestion of sort of how many parameters is too many parameters in the model. And then the other things that you want to look out for are things that are super, super multimodal, things that might have really, really strong correlations, although these algorithms are supposed to be really smart about dealing with real degenerate parameter spaces. Anybody else think of any pitfalls? Yeah, okay. So something like, 10-ish parameters and with like some mild covariance matrix, right? These off-the-shelf samplers will just plow right through that, no problem. When you get up to hundreds or thousands, it's probably on you. That's my rough estimate. Individual results may vary.
Thanks.
Yep.
So from what I understand, the output of nested samplers don't have any fundamental ordering of any of their samples. So how would you calculate an autocorrelation link?
Well, if it's they're ordered by likelihood, right? Maybe, maybe not. Pat, do you know the answer? Or are you stretching?
I think that you sort of do it as you generate the knowledge point. So I think that something like, maybe not Dynasty, but like the CPNet, for example, they run like an MCSD chain to generate the knowledge point. So they require the likelihood of larger, but they also require the autocorrelation that short MCSD knowledge point is smaller than the number of steps you taken. And so sort of when you do it that way, I think to get something that is okay. That's the general idea. And I think that's discussed in the skilling and skilling they suggested 20 samples or something like that over time. But there are ways where you just make sure you don't
Okay. Did you have one?
Quick question. So we go through all the trouble of finding evidence, but that number doesn't mean anything on its own, right? Because the evidence that you calculate needs to be compared to evidence from another model. So is there anything that I'm missing in here that we want to calculate just one Bayesian of just one evidence for one model? Because in my mind, we want to compare two models, and there might be a clever way of calculation that can happen, because all we care is this model preferred over the other one, or what's the versa.
Right. So you're right. So if I have just a single model, the evidence is a waste of time because it's a likelihood, and the likelihood doesn't tell you anything all by itself. It's a relative measure. So you need something to compare against. So if you have several models, then right, you calculate the evidence for each one of those models and then weigh them all against each other. And that still does not give you an absolute measure of how good your model is. It just tells you which of your models was the worst. Right. You're not missing anything. By itself, it's useless.
So if I'm understanding correctly, basically as you go through your nested sampler and you keep iterating, the entire volume gets smaller and smaller. So it seems like as over time, it would get harder and harder to like propose like a new sample that is like a higher likelihood. So I guess is there a way that's naturally accounted for in this sampling so that we can like continue generating samples new samples efficiently, or is that kind of something that goes with?
So I think when you're writing nested sampling algorithms, that's one of the things that you're thinking really hard about is how you do those updates. And if you just use a naive MCMC, then you're right. As you get deeper and deeper into the number of iterations, your naive MCMC is going to become less and less efficient. But there's no rules that say you have to use an MCMC for how you update the live points. So maybe you use something like what MC does, which is using all of the live points together to generate a proposal to say, jump along gradients there. So it doesn't have to be an MCMC. That's just sort of, one way to think about how you would do it. It probably works pretty efficiently at the beginning, and maybe you want to transition to something later. I don't think the way you update the live points is subject to the same strict detailed balance conditions as the way you use an MCMC. I guess there's a pitfall if things are super, super correlated with like what Pat was just talking about, but you can cook the books a little bit more when you're trying to update those live points. You don't have to worry about being as strict as an MCMC. Am I saying anything totally wrong here? Okay.
That's my experience with method sampling anyway, but it starts off iterated very quickly, and then for problems that are beyond, say, 30 dimensions, or maybe even just like 20 dimensions, it can spend days to weeks just trying to accrete that last tiny unit of log evidence when it's going along. And so, there's like an industry of people trying to work out how to optimize that. Multina's used rejection sampling, like the ellipsoidal volume bit. Polychord, which I don't know if it's actually still being used anymore, but it was TempoNest actually. It used to be slice sampling, and then Alterness and Becsy. I don't know exactly what they're doing under the hood. But there was an effort, I think, from some people connected to LIGO 10 years ago, to actually train a neural network as the nested sampler was proceeding, and it would learn the likelihood surface, so that once it got to that last little unit of log evidence, it just went like that, because it could already it already knew the shape and how to get that integral. I don't know if that's still being used. It's called Bambi, still graph and some others.
No, it never. It got close, but it never made it over the fence.
Yeah. So I don't know if that's still being used as a general technique for that sort of thing, but it is really hard and dispiriting when you're watching, hoping that it will get there, and it doesn't quite get there.
Anything else? Someone has said, yeah.
It might be not a very clever question, but when what we were missing at the beginning was the posterior. We didn't know what it was, so we used the likelihood and prior to tackle the posterior, and we skipped over the evidence. But after the NKFC is done, now we know the posterior. We already know prior, we already know the likelihood. So why can't we just tackle the evidence by the sample fraction?
So you don't know the posterior. You have a set of samples from the posterior. And if it's a trivial enough parameter space, let's say it's just like a two-dimensional parameter space, you can do some sort of like kernel density estimate and then try to integrate that to get the evidence. But that gets worse and worse as the dimension gets larger and larger. So if you have a really high dimensional parameter space, now you have finite samples from 100-dimensional space. I don't know how to do a good job of integrating that just using the finite samples that I have. A KDE in 100 dimensions is no good. So on small enough spaces, you're right. You can use those samples to estimate the integral. But once dimension gets large, it's no longer a generic way to go about it. Okay. I'm here all day-ish. Thanks, everyone.
Okay, we can take a break until 11 o'clock when Bence will take over with the tutorial. And if you want to get his notebook and material for the tutorial, just do a fetch from the repository. Right now. Hi, Bence. We're just filtering back in here after the break. We'll get started with your tutorial in a minute or so, okay?
Can you hear me okay?
Yeah, can hear you okay.
Awesome.
We'll get started in a minute. All right, I think that's most people back in the room. You've now heard some angles on the theory and the idea of practical implementations of Bayesian statistics from Tyson today and Neil a little bit yesterday. But it's now my pleasure to introduce the newly minted Dr. Becsy at Montana State University. And I hope I get this correct, moving soon to be a postdoc at Oregon State University. Excellent. Okay. And so Bence is going to give us a tutorial and a guide through the implementation of some of these Bayesian techniques. So whenever you're ready, Bence, please go ahead.
Great. Thanks, Steve. Let's see if I can share here. Can people see that? Yeah, okay, I see hands up. Okay. Cool. Yeah, so in this little tutorial, we'll further zoom in and we'll just focus on one part of what Tyson was talking about. We'll focus on parameter estimation with an MCMC. So I have a little notebook up in this GitHub repo. So if you want to follow along, you can go to week 1 and day 1. You can download this folder or the notebook itself just. And yeah, so I have a little name here, encouraging everyone to think about Monte Carlo methods and how they can be used for practically anything. So it's just a little motivation. And so in this tutorial, we'll kind of go through a very simple toy problem. So you'll generate and analyze a simulated data set with just a simple sine wave and Gaussian white noise, and go through building an MCMC and everything for it. So first off, we need to import some stuff. So I think one kind of not very standard packages here are corner and MC, but I think those should be in the PTA install package that everyone should have installed. But if not, then you can hopefully just uncomment here some of these and just pip install them. I just realized now that I started that maybe some of these like Jupyter magic things are not standard stuff, but I think we won't need most of them. I just copied over. So you can just comment them out if some of them gives you errors. And yeah, so with that, we can get right into it. So as you heard in Neil's and Tyson's talk, do a parameter estimation. The main ingredients we need are, in the signal model, and then we will need a prior function and the likelihood function. So we will build these, and then we will go on to actually building an MCMC to sample this problem. So as I said, we will look at a simple sine wave in Gaussian data, Gaussian noise. And so our model just looks like this. It has an amplitude and a cosine and 2 pi frequency times a time series and some initial phase. So this will be like a discretely sampled time series, of course, and then our signal is a discrete time series as well. And you can see that there are three different parameters here. So we have an amplitude, we have a frequency, and we have an initial phase. So those are the three parameters that we will sample over in our MCMC. So to start off, we need a function. We need to define a function that will give us this simple signal model. So I have that here. This will take in the time series, the observational times when we want to evaluate this model, and then the three parameters the model has. And it will just return another time series, another array in this case. So then we go on to actually generate our simple data set. So our data series will just look like the signal plus some noise. So we take some parameters for the signal, for the amplitude, the frequency, the phase, and we set up some observation times where we sample this. And to generate our data, we just take this function, plug in these values, and then add random Gaussian noise with a mean of 0 and a variance of 1 with this numpy.random.normal function. And then we can plot both our data and also just the true form of the model we used here. So if we do that, you can see that these data points are actual data in this D array that we will analyze. And then the true model we used to get it is this black line. So it really just looks like what it is, a sine wave and some noise on it. So then we go on and we implement our prior and likelihood to have those for the MCMC. So the prior we will use a really simple prior here. It will just be a uniform prior on all the parameters. So it's basically will be 0 if the parameter value is outside the prior volume. So that will restrict these parameters to some range. And if it is within the prior volume, then in order to be normalized, this will be just 1 over the parameter ranges in all three of these parameters. So the actual implementation is not much more complicated than that. We usually work with log likelihoods and log priors. So we will do that. We define this get ln prior function, which takes in numpy array. And then just for clarity, we can convert the elements of this array into these three variables. So it's easier to see which element is which. And let me just hard code some lower and upper boundaries for the parameters here. So for amplitude, I just did between 0 and 5. For the frequency, I did between 1 and 10. And the reason I didn't allow it to go to 0 is just, funky things happen when you have a sine wave with 0 frequency. So it's better not go all the way down to 0. And for the phase, it's pretty trivial that you want to do between 0 and 2 pi. And then the main part of this function is just, it checks if these parameter values are within the prior bounds. So it checks the amplitude is larger than the minimum and smaller than the maximum. Same thing for the frequency and the phase. And if so, it returns the natural logarithm minus the natural logarithm of these prior ranges, which is your prior. If not, then it returns minus infinity because in log space that corresponds to a prior equal to 0. So let's run this cell too. And then it's probably a good idea to test your prior function just to make sure that it makes sense. So here I just plugged in some parameters that should lie within the prior bound, the prior ranges, and then I just print the log prior for that value. And I also print one that I calculated by hand here, which is just 1 over 5, which is the amplitude range, over 9, which is the frequency range, over 2 pi, and taking the log of all that. And so these two should match up. And then I also look at a point which is clearly outside of the prior. It has a negative amplitude, and so that just should give us -infinity if everything is right. And you can see that these two values match up, and the third one is -infinity. So it looks like the prior is working fine. So then we go on to building the likelihood. That is not much more complicated, maybe a little bit. So I think we've seen this equation maybe in Neil's talk yesterday. So when you write the log likelihood in Gaussian noise, what we do is that we take our data and subtract the signal model. And so that should be an estimate of your noise. And so if you take this inner product between that data minus signal and itself, take a -1/2, and that should give you the log likelihood. And so when you write this out, you have 3 different inner products with data and signal, signal and signal, and data and data. And the way we define here the inner product is that we are just working in the time domain here, so no FFTs, anything. So, and we have n data points, and we just assume that the noise is a white noise with a uniform variance over all the observations. So our inner product is just, sum over the product of these 2 series and divided by a variance that we will just fix here. But in principle, you could also make that a parameter of your MCMC and sample over as well. So to build this likelihood function, we need to define an inner product. That's very simple from this equation. We just define a fixed sigma. In this case, because we generated the data in a way that the variance of the noise is 1, we just fix that here. So that's easy enough. And then we return the sum over this product, and just divide it down by the sigma squared. And so then to get the log likelihood, we separate out these parameters as in the prior, just for clarity. Then we calculate the signal based on these times that we plug in and these parameters. And then we calculate these 3 different inner products, and then we just return the proper combination of them to get the likelihood. Yeah, I ran everything. Okay. Yeah, and so before going into building MCMC for this, it's a good idea to have some consistency checks for the likelihood as well. So what you can easily do with this small number of parameters is just define a grid, let's say in frequency, which goes over the whole prior range, and you can just calculate the log likelihoods in a way that you fix the other 2 parameters to their true values, and then just loop over the different values of the frequency over the whole prior range, and then you can plot the log likelihood. And you can see here that we put in a signal with a frequency of 2 Hertz, and it has the likelihood surface is a nice peak around 2 Hertz. So probably we did do it right. So it looks all right. And then you can do the same kind of thing with the amplitude and the initial phase. And you can see that the amplitude is nicely peaking close to the true value as well. And the initial phase is doing the same thing. One thing that you can see already here is that your frequency, it's kind of a very sharp peak. So the frequency will be very well determined in this problem, but the amplitude is kind of a much wider likelihood surface here. And similarly for the phase. Another interesting thing about the phase is that there's sort of also a minimum here, which is just a pi offset from the true value. And that's, just basically putting a minus sign on your whole signal. And then you get like completely off phase. You are really not matching your signal at that point. That's why there's a minimum there. So that we have all the ingredients to build an MCMC and sample this problem. So what I plan to do here is that I have a skeleton of an MCMC here, and we will go over what does this need, and I will give people maybe like 10 or 15 minutes after this to play around a little bit with it and maybe implement some parts of it, this MCMC. And then I have a solution for that, and we can go over that. And then there's also some post-processing after running the MCMC. So this looks like we have a function I called run MCMC that takes in 4 different parameters. 2 of these are just the T and D arrays that we need. This is basically the data we use, and we need those for the likelihood calculations. Then we have a number of iterations to run for. That's pretty self-explanatory. And then we have a covariance matrix that we use for the proposals. So the plan here is that we will use simple Gaussian proposals. So what we will do is we have this covariance matrix, and then we will take the eigenvectors of that covariance matrix, and we will propose Gaussian jumps along those directions. And this function in the end should return the posterior samples, which will be an n by 3 array because we have 3 parameters, and we have 1 sample for each of our n iterations. It will also return log likelihood values for each of these samples. That will be this is not true. This will be a length n array actually, because for all the samples we will have 1 log likelihood value stored. And then we will also return an acceptance fraction, which just keeps track of what fraction of the proposals are accepted. So that's a good diagnostic thing to keep track of, because we will see if something goes wrong, then we won't accept any of the proposals, or we will accept all of them, and that points us in some direction of what could go wrong here. So the first block that's missing here that you will need to code up, and it should be very simple, is taking this covariance matrix and just using, there's a numpy function for that, just taking the eigenvalues and eigenvectors of that covariance matrix, and then building these 3 vectors, which should be the eigenvectors scaled with the square root of the eigenvalues, and those you can show that those are good. If your covariance matrix is the true covariance matrix of your problem, then those will be really good proposal vectors to jump along. And Then I kept that in here. There are set up arrays for the samples and the log likelihoods to keep track of those. Then what you will need to write here is, just take this samples array, and for the very first slice of it, put in an initial sample where we will start from, and that could be just, whatever point you just hard code in here, but it could also be just drawing a random sample from the prior. That's probably a better idea, but it should be fine starting from just any point in this simple scenario here. And then I also have a place here where I set up these AES and ANO arrays, and these will be used to keep track of acceptance rates. So these have 3 elements for the 3 different directions that we are jumping along. And so what we'll do is whenever a jump along one of those is accepted, we will add 1 to the appropriate element of the AES. And when it's not accepted, it's rejected, then we'll add to ANO. And so that way we'll keep track of how many of the jumps are accepted in each of those eigendirections. And then we have here the mean loop of the MCMC after everything is set up. So this will just loop over n number of iterations, and this just prints out the number of iterations 10 times over the whole thing, so that we know that it's running. And then there's a bunch of stuff here that you will need to code in, but most of this should be really simple. So this one, just, we have those 3 eig vectors here, and we want to randomly decide which one we want to jump along. So here we will just draw a random number, and based on that you can decide which of those eigendirections you want to jump along. Then we use that eigenvector we picked to actually select a new point based on this proposal. So the way we'll do that is that we will just take the current point, which we can read out from this samples array, and we will add to that, we will add the eigenvector we picked multiplied by a unit normal number. So yeah, then we have the new proposed point. So to get the Hastings ratio, we will need to calculate the log likelihood at this new point. So this here is really just taking this new point and calling the get ln likelihood function on it. And then we actually need to calculate the acceptance probability. And in this example, this proposal, it just has some direction and then a random normal distribution on it. So it's a symmetric proposal, so we don't need to worry about putting those into the acceptance rate. So I think this is was one of Tyson's simple examples when everything just cancels out and it's a very simple acceptance probability. And so what we will need to do is it will just be the ratio of the likelihoods and the priors, but since we are working in logs, it will be just the difference in log likelihood and difference in log prior, and then we will exponentiate that to get the actual probability value. And there's the step where we decide if we want to accept or reject this step, and the way to do that is that we will draw a random number between 0 and 1, and then compare that random number to this acceptance probability. And so if the acceptance probability is smaller than the random number, then we will, wait a second, or is it the other way around? Yes, if the random number is smaller than the acceptance probability, then we accept the new point, and if not, then we reject it. And the way we use this, you don't even need to do that extra step that Tyson talked about, where you take the minimum of 1 and your Hastings ratio, because if this acceptance probability or Hastings ratio is larger than 1, then your random number between 0 and 1 will always be smaller than that. So that just takes care of that. So it's not a problem if this is larger than 1 in this implementation. And so if you accept the proposal, then you will add to your samples array this new point that we proposed, and add the new log likelihood we calculated to the array of log likelihoods, and add 1 to the AES array. If not, then we will just copy over the previous sample and previous likelihood and add 1 to the ANO array. And so this concludes this loop, and then we just calculate this acceptance fraction, which is the number of accepted steps divided by the total number of steps, and then we return all of these. So yeah, so I think my idea here was that you can take 10-15 minutes to play around with this, and then I have probably another maybe 20 or 30 minutes worth of material after that. But in the meantime, I'm also happy to answer questions for the stuff that we looked through so far, or if anyone is trying to do this and get stuck, I'm happy to help. There's also, oops, I should probably hide this. There's also my solution in the next blog. So if you are impatient and don't want to wait another 15 minutes, you can just take a look there. Yeah. Is there any question for the thing we covered so far?
Any questions so far? Or anything online? Okay, then Bence, you said about 15 minutes to work on up to this point.
Yeah, I think that sounds good. We spent like a half an hour so far, right? So yeah, maybe 15 minutes. And then, as I said, I have maybe 20 or 30 minutes more after we have the MCMC done. So I think that should put us in a good time frame.
Perfect. Okay, so we'll work on our own here for 15 minutes and come back at quarter to the hour.
Okay, I'll be around if anyone has any questions, either in the chat or speak up or anything.
Okay, Bence, would you like to take over again and lead people through the rest?
Sounds good. Yeah. Okay, so let's have a look at my solution here. So, yeah, as I said, it's really easy. You just have a numpy linealog.eig. You can get the eigenvalues and eigenvectors of the covariance matrix. And then the way we want to use this is that we take the three different eigenvectors we have. And those are just stored in this matrix form. So to get from the eigenvectors, you just take a slice through that. And then we need to multiply that by the square root of the eigenvalues. And that's just because that's basically corresponding to 1 sigma, because these are covariance matrix. So everything here is like in terms of covariances and variances. So when you take the square root of that, that's basically kind of like a sigma. So these will be just like 1 sigma jumps along the eigendirections of the covariance matrix. And then to set up an initial point in our samples array, I just do random draws from a uniform distribution, because that's basically our prior here. And alternatively, you can also just plug in whatever numbers to start from, because it's not a very complicated posterior. So you probably will be fine wherever you start from. Yeah, and then we also get the log likelihood for this initial sample, and just put that into this log likelihood array as a first element. Yeah, and then we do the loop over iterations. So as I said here, we randomly select an eigendirection to jump in. So here I just used numpy random choice, which just gives you, with this argument of 3, it will give you 0, 1, or 2 with like equal probability. So if it's 0, I just put the first eigenvector we defined into this jump array. If it's 1, I put the second one. If 3, I put the third one. So that way, in this jump array, I will have a randomly selected eigenvector. And so to get a new point, a proposed new point where we will try to jump, I just take the current point in the samples array, which is just the ith slice of it, because I is the index we are looping through here. And then I just add jump times a random normal distribution, which without arguments will just give you like a unit normal with like a unit variance normal with a mean of 0. So yeah, so we have a new point where we try to jump to. We get the log likelihood at that new point, put it in this variable, and then to get the acceptance probability or acceptance ratio or Hastings ratio, we just took the difference of the likelihood. So the likelihood in this new point minus the likelihood we stored from the previous point, plus the likelihood in the prior in this new point minus the prior and the point we've been before, and then exponentiate that, and that's our acceptance probability. So then to decide if we actually want to do this jump or stay where we are, we draw a random number with random uniform, which will give you a random number between 0 and 1. And if it's smaller than is acceptance ratio, then we accept the jump. If not, then we reject it. And so if we accept it, we just copy in this new point into the next I+1 slice of the sample array. If not, then we just copy over the current slice. And if we accept it, we put in this new log likelihood into the log likelihood array. If not, then we just copy over the one from before. And if we accept it, we increase the element, the proper element of this A jump array by 1. If we don't accept it, then we increase the element of this A no array. So that's all there is to it. And yeah, so to actually run this, we need to define the covariance matrix. And in principle, you could find that in different ways. You can take like numerical derivatives of the likelihood and approximate it that way or things like that. But here we just make a guess, and that should probably work for this very simple example. So I just do a diagonal covariance matrix. So we will jump in the direction of the parameters. So you'll only change one parameter at a time. And I just put different variances for these different parameters because, as we've seen before, some of these will be more constrained than others. So you can play around with choosing different covariance matrices, but I found that this one works fairly well for this problem. Yeah, so I picked 100,000 iteration number here, and that should take a few seconds. So if you run this, you can see that we printed out the eigenvectors that we are jumping along, because there's a square root in it. It's different than just the slice of the covariance matrix. But yeah, you can see that we are jumping in. What is the first one? Is that? I think that was amplitude. So we are jumping scaled by 0.3 in amplitude, 0.1 in frequency, and 0.3 in phase. And yeah, it ran through in like 30, 40 seconds. Yeah. And so now we have our samples in this samples array. And then there's a bunch of different stuff that we can do with those samples. So there's a bunch of different processing things we can play around with. So one thing is kind of the reason why we tracked all these acceptance fractions, but we can take a look at them, and you know, there are definitely some like math papers saying what is the optimal value for your acceptance rate, but like as a rule of thumb, you know, it definitely should be higher than 0.1 and smaller than 0.9, let's say. So, you know, because if it's less than 0.1, then basically you are never accepting your jumps. So you are just wasting computational resources for trying jumps that you won't accept. If you accept them all the time, then, you know, you basically lose the ability to explore the posterior. You are just doing a random blocking parameter space. So yeah, you definitely want them to be reasonable values, not close to 1, not close to 0. And here, I think these look fairly good. Yeah, so I think this is nice. Another thing to do as a diagnostic is to do so-called trace plots. So here we are just, oh, this actually looks fairly bad. Maybe I should do a longer run. Let's just do one as I talk. Yeah, so what you see here is that these horizontal lines plotted here are the injected parameter values. So we would want to see these are the parameters as we move along in the iterations. So you would want to see these converged to these two values, and then just moving around those. Yeah, I guess with these jumps, maybe it just gets stuck into a minimum. Last time it worked for me, so hopefully a longer run will be better. Yeah, and so hopefully this will happen now, but Well, it's better. For some reason, it finds a different frequency. I'm not sure why. Yeah, but what you usually see is that it has some iteration where it's just kind of exploring and didn't lock onto something yet. That's what we usually call the burning period. And we usually just cut that first chunk of the samples when we do any kind of inference later on. So yeah, this is actually interesting. I'm not sure what it's picking up, but it's definitely picking up something else. But yeah, it's actually a good exercise to see what went wrong. Yeah, so another thing to check is you can calculate autocorrelation length, because we want these samples to be independent samples from the posterior, but of course they are not. There will be some correlations between subsequent samples. So it's a good idea to calculate the autocorrelation length, the integrated autocorrelation length. That will tell you something about how many samples actually constitute one effective independent sample. So you want these autocorrelation lengths to be as small as possible, so that for a given number of iteration, you will get more information out. So yeah, you can see that the amplitude and phase is really nice low correlation length, but for some reason the frequency is very correlated. So maybe that tells us something about what went wrong here. Yeah, another kind of visualization is that even in this three-dimensional problem, you cannot really plot the three-dimensional posterior distribution of in the parameters, and it's even more true for like hundreds of dimensions. So what we sometimes do is that we plot something called a corner plot. So this will show, let's just run this. So this shows like a grid, and on that grid, you have the one-dimensional marginal posteriors for each parameter in the diagonal. So this is the marginal posterior for the amplitude, for the frequency, and for the phase. And then on the off diagonals, you have the two-dimensional marginal distribution for each pair. Yeah. And here I also plotted the true values for these parameters, and you can't really see them because they are fitting something else for some reason. One thing you can try here is that, so there's this range parameter that you can plug into corner, and to that tells it what ranges to use in the different parameters. So what this does, when you just give a number for each parameter, then it tries to pick a range so that it fits that fraction of all the samples within that range. But instead, we can try to plot this for the whole prior range. So if you give these little tuples for each parameter, then it will use those as ranges. So we can see that for some reason, it's really interesting. I'm not sure what's happening. For some reason, we are finding something at higher frequency, but lower amplitude, which is kind of weird. Yeah, and you can see that there's some multimodal structure in this. Okay, another kind of diagnostic that might help us see what's happening here is that we can plot something called the basogram. So this will, in the previous plot here, we just plotted the distribution of all the parameters. But what we can do instead, which sometimes is more informative, is that we can calculate the actual waveform, the form of the signal for some of these samples, and we can actually plot them, and then we can see not the distribution of the parameters, but the distribution of the signal they are describing in the data. And we can overplot that with the data as well. So here I'm just plotting the data and then loop through 30 randomly picked instances, and I will plot how the signal would look like for those randomly selected posterior samples. Yeah, so it's definitely picking some lower, so you can see all these little lines, right? So they are kind of fitting something that I don't really see in this data set really, so I'm not sure what's happening, but yeah, it just gets stuck in a local maximum here. So yeah, and another thing you can do is that you can, or kind of diagnostic, is that you can calculate something called the match between the true signal that you simulated and the recovered signal for some random draws from the posterior. So this match is defined as the inner product between the injected and recovered signal, and just normalized with the inner product of the signal by itself and the recovered signal by itself. So that this match is always between -1 and 1, and the closer you get to 1, the better you are recovering the true signal. So I previously tried it. This gave like matches of 0.99 or something. So maybe now that we are totally off, then this will give something different. Yeah, so we can see that the matches are very close to 0, 0.15, 0.2. So yeah, something is clearly going wrong here. So I guess one thing here is that this was a very simple MCMC that didn't have parallel tampering or any more informative, more nuanced proposals. And this simple proposal that just jumps along the current point is very prone to getting stuck in a local maxima. So let's just try. One thing that might help is to increase the jump sizes, so it's easier for it to jump out of the local minima it gets into. So let's just increase everything in variance by a factor of 10. And so that should increase the jump sizes by like a factor of 3 or something. And maybe that will help.
Maybe if this is still happening, Bence, just a grid scan, because you're dealing with a low dimensional problem, just to visualize any multimodality, or just scan the likelihood across frequency space and see what it looks like.
Yeah, that's a good idea. So I mean, we did some of that, right? And so up here we had just one-dimensional slices of that. And what I'm thinking about, so what we are thinking about is like a frequency of 3.5 or something instead of 2. So let's see, and this thing, yeah, there's definitely a small maximum at 3 point something. So I guess I really want to fix this the easy way. I can just make our sampler start from the actual injected values, so that it will definitely find it. But I haven't seen it before when I played around, so I hope that just increasing the jump sizes will help. So increasing jump sizes, so the acceptance fraction went down significantly. Let's see. Okay, it found the signal now. So now you can see that the amplitude is right on top of the injected value, frequency, and phase as well. So, and we have a very short learning period, and then it finds this thing. So I guess this is a good lesson that there's kind of a balance between between having big jumps and small jumps. So that sometimes the big jumps are, this is definitely not an ideal acceptance rate below 0.1, but then it helps explore and find the signal. So I guess one thing that you might want to do, and I think even PTA CMC sampler does that it updates the covariance matrix as you move along. So you might want to start with a covariance matrix that promotes large jumps, and then as you kind of lock onto the signal, then you might want to decrease that jump size so that you can effectively explore that peak. And so let's see the covariance, like the autocorrelation length here. Yeah, they are all fairly reasonable now. And if you do the corner plot again, yeah, now that peaks where it should. Maybe we should change back now to doing this automatically, finding the right thing. Yeah, and you can see it's really nice. Almost looks like a Gaussian posterior here. The reason why it's good to use these corner plots is then you can see that, for example, between the frequency and the phase, there's a clear correlation, quite strong correlation between the two. So that's interesting. And hopefully, if you redo this Bayesian now, yep, now you can see that it's nicely follows those data points. So it looks like even in this small three-dimensional problem, it's sometimes hard to find the maximum. And then if we calculate the matches, you can see that it's basically peaking at 1, and most of the values are about 0.98, so really good match with the injected signal. And yeah, I also calculated the signal to noise ratio here, so that's just the inner product with the injected signal with itself and taking the square root of that. So in this case, that's like a SNR 17.6 signal here, so a pretty strong signal in this case. Yeah, the other thing I have here is a very simple way of estimating base factors. So we didn't do like a transdimensional thing here or anything, and there's probably no time to go into like thermodynamic integration in such tutorial. But one thing that you can do, which I don't think Tyson talked about it, but maybe Neil mentioned, I'm not sure, is the Savage decay density ratio. So if you have two models you're trying to compare and you get back one of the models by setting an amplitude in the other model to 0. So for example, in this case, we are trying to compare the model where there's a sinusoidal signal in the data set versus it just being Gaussian noise. So in this case, if we set the amplitude of the sine wave to 0, then we get back the other model where there's no sine wave, right? And so in these kind of nested models, you can approximate the base factor by taking the ratio of the prior and the posterior of your amplitude at the value of 0. There's kind of a proof of that, but it kind of makes sense, right? So if you're on your MCMC and you have very low support at 0 amplitude, so your sampler says that there's no chance that the signal has 0 amplitude, then that means that there's strong evidence for the signal being in your data set. So what you can do here is that we can get the amplitude posteriors and then make a histogram of them. And then we can just look at the very lowest amplitude bin as an approximation for the posterior at amplitude 0, because of course we cannot really measure it like a perfect example, but we can just look at the very first bin and then compare that with the prior. So if I do that, you can see that our posterior peaks around 2.5, which is the injected value. And this is the prior. And the problem with this kind of thing is that, this is a very strong signal. So we basically have no samples at the very lowest amplitudes. So when we calculate this estimate for the base vector, it just gives us infinity because we are dividing by 0. So you might be able to play around with this and like change the amplitude of the signal to something smaller and get a reasonable base vector estimate here. Yeah, but for these stronger signals, you definitely need to do something else to get the base vector. So that's kind of what I was hoping to cover here. I listed a few ideas here that you can try with this notebook. So there are some very simple ones like playing around with the signal, having different amplitudes and different frequencies and see how things change there. You can also do a thing where, so now we added noise to the signal. You can also analyze a data set where there's no noise, just the signal itself, and see how the parameter recovery changes in that case. I guess you can also try to just analyze noise without any signals, and then you definitely should get here an amplitude posterior that peaks around 0, and then you can have a base vector for having a signal in there. Then you know that there's no signal. One signal to noise ratio, but you can also try to compute that for random draws from the posterior and see how it compares to the injected to signal to noise. What else? Yeah, you can also play around with the covariance matrix. One thing that might be interesting to try is that instead of the diagonal thing, you can maybe try to approximate the covariance matrix from the results of a pilot run, right? So we've seen in these posteriors that there's definitely correlation between these two parameters. So if you can approximate this correlation from these posteriors, you can put that into your covariance matrix and use that for your proposals, and that will definitely work better because then it will jump along this most correlated axis, and it will export this whole thing much better. And what else? Yeah, another thing I mentioned before is I think another reason why this base vector thing works very poorly is that we just fix the noise level in our model. So ideally, you would want to include the noise level as a parameter, and then instead of putting in a signal, it can increase the noise level and kind of soak up the signal that way. And I'm pretty sure that we would have better support at low amplitudes that way. And there are some other things to try if you really want to get into things. You can add different proposals to this CMC we built here. It's really easy to put in a draw from the prior because we already do that to set up the initial samples, and that should be easy. And you can also get crazy and add in differential evolution or some global proposal. Maybe you can base it on just an FFD or the PSD of the data. That should work nicely, or add parallel tempering or things like that. So, the list goes on and on. But yeah, these are just some ideas. And yeah, I'm also happy to answer any questions or if anything didn't make sense from this whole thing.
Thanks a lot, Bence. Anyone got any questions? Tyson,
I have two comments. The first is that the number one mistake I've seen when people write their first MCFC is to forget to record the rejected samples. So up in Bence's example MCMC, where you're explicitly saving the sample, if you, yeah, there we go. That one's a really important step. That one that seems a little counterintuitive, but you basically end up with repeated samples in your chain, which is obviously then going to have a lot of correlation. And that's why at the end of the day, you have to thin the chain to get rid of those correlations that you introduce by having repeated samples. So remember that one. And the other comment is that the Savage-Dickey density is not an estimate. It is the Bayes factor, which is awesome because it's like the cheapest way you can ever end up calculating Bayes factors. But the trick is you only get to use it in very limited examples. But if you have nested models and not too many parameters, that should be your go-to because that one is right all the time. That's all.
Yeah. Well, I think the point where it becomes an estimate is that you are using a finite bin to find the amplitude at zero. So I guess, yeah, that's where it becomes an estimate, but yeah, otherwise it should be great. And the other thing that reminded me, what this thing reminded me of is that one thing that it's kind of a small thing, but I've been doing this the wrong way for a very long time. And I think no one ever told me because it was so trivial, is that we are sometimes, it's a good idea to log to keep track of the likelihood values. Then when you calculate your acceptance ratio, you only ever need to calculate the likelihood for the new point because you already have it for the old one. But in some of these tutorials, people just say, okay, calculate the likelihood for a new point and calculate for the old point. But since you already calculated for the old point, it's really a good idea to keep track of those and just use them from the array, because otherwise, it will be like 2 times slower usually. So, yeah.
Any comments or questions online? Can't see any hands up. Well, on the Savage-Dickey ratio, one technique I've seen actually from the Tyson and Katarina and Neil is if your signal is a bit strong and you don't have good sampling of the posterior down to 0 in the parameter space that you really need, then you can do kind of segmented runs where you'll focus in on that part of parameter space, and then you just kind of chain everything together at the end in order to get information about posterior down in the low probability regions.
Yeah, that definitely works. Yeah, so you can just, you get these samples and you can like take the, 10th percentile of it and just take that as the upper limit of your prior bound for the next run. And then you will go further down and down. So you repeat that, and then you just need to take those factors into account when you calculate the Bayes factor in the end. So yeah.
Although to be boring, when it's a Bayes factor of a quadrillion to 1,
Do you care?
do you care, right? It's in this example, right? It's like 10 sigma. We're good.
Yeah.
Yeah, although in this example, I guess, if you just look at the data, you probably don't need an CMC to say that there's a sinusoid or something in there. So, yeah.
All right, I'm not seeing any more hands up in the room. That might be because people have been dazzled by the presence of lunch. So, Bence, thank you very much. That was a great introduction. Let's show our appreciation. All right, well, you can sign off anytime, Bence, or we're just going to be hacking later this afternoon. But if you need to ask Bence any more questions, you can tag him on Slack.
Definitely. Yep.
All right, well, before you get lunch, we're going to try to take a group picture outside. And we'll do that really, really quickly because obviously the lunch is right there. So why don't we just stop recording, stop streaming on YouTube, and then we'll just head out to the courtyard and take a quick picture.